Let's start our notes for section 2.10, the definition of the derivative. So we're going to start by thinking about something we saw in section 2.9. This section was about instantaneous velocity at a particular time, or also average velocity over a time interval. So in that section, the function f of x or f of t, the original function, it had to represent position, so some sort of distance measurement probably. And in that case, the definition we had for instantaneous velocity at some x value was this right here. So it was the limit as x approaches whatever number a is. And then we have the slope formula between x f of x and a f of a. All right, so in this section, we're going to take away this requirement right here. So if f of x is just a regular function without context and doesn't represent position, we're going to use this definition and just kind of interpret it in a slightly different way. And that brings us to a really important definition. All right, so this definition is for the derivative. The derivative of f of x at x equals a, denoted, so this is just like a little tick mark, almost like an apostrophe or single quote after the f. We say this out loud, f prime of a, and in an actual example, the a is filled in with a number, so this will be like f prime of 2, f prime of 0. So this is given by the exact same definition that we have above. So now we just have a new name and notation for it. So instead of talking about instantaneous velocity, we're just going to call it this derivative thing here. And this is the derivative provided that that limit exists. If the limit exists, we'll say that f is differentiable at that number. And if the limit doesn't exist, we'll say that the function is not differentiable at that number. All right, so this is a really important definition for us going forward. This is the big takeaway. The derivative, this f prime thing, is going to be surprisingly important. It's something that we're going to be talking about for the rest of this class, one way or another. All right, so this brings us to our first of two examples. So we have a function 2x squared plus 3. It doesn't represent anything special or position. So instead of instantaneous velocity, they just say compute f prime of 1. So I'm going to use this new definition and fill in a 1 for the a. And that's actually my first step here. F prime of 1. I'm going to write this exact definition, but with a 1 filled in for the a and nothing else changed just yet. So I have f of x minus f of 1 over x minus 1. So this definition with the a's turned into 1s. Okay, and now the denominator here is set, right? X minus 1 is going to be part of my formula. I have my limit actually set with a number. What I need to actually fill in for this example is the f of x. That's going to be 2x plus 3. This whole thing goes in for f of x right here. And then f of 1, I need to actually compute for this function. And this will just be a number. I'm going to plug 1 into this formula. And I get 5. Okay, so we'll put each of those things in their spots. That gives me limit as x approaches 1 of 2x squared plus 3, that's my f of x, minus 5 over x minus 1. Okay, so I'll clean up my numerator here. Plus 3 minus 5 is a minus 2. So I have 2x squared minus 2 over x minus 1. And now I just have a limit problem. So I can switch into limit mode. And I say, okay, if x is approaching 1, let me just try to plug in 1 and see what happens. And if I do that, I get 0 over 0. All right, so that's my limit type, 0 over 0. So that tells me one of 3 techniques is going to work here. If it's polynomials, we factor and cancel. If it's fractions, we use an LCD and then cancel. And then if there's a square root, we'll do the conjugate trick. This one is the first of those 3, right? Because the top and bottom are both polynomials. So I need to factor my numerator. So I'll pull out the 2. And I have x squared minus 1 left over. And while this looks really similar to the denominator, I can't really cancel anything yet because of this square is making them different. But x squared minus 1, I can factor. And if you don't see it, we could always think of it as x squared plus 0x minus 1. You think, okay, what two numbers multiply to -1 and add to 0? +1, -1 will do it. So I'll continue down here. The 2 is still on the outside, and I have x plus 1, x minus 1. So positive and -1, they multiply to -1 and they add to 0. On the bottom, I have x minus 1. And then I can see the x minus 1's top and bottom that cancel out. And that's what was actually stopping me from plugging in 1. So now I can just plug in 1 for the x's that are left. And I get 2 times 2 is 4. So I would say f prime of 1 equals 4. So that's my answer. And because this limit actually computed to a number, that means it exists. So you could use some of this other new vocab to say this f of x is differentiable at 1. All right, let's try one more. I have a different function type for our second example, but otherwise it's going to go the same way. So we have a new function and then f prime of 3. So I'm going to start by writing this f prime of 3 derivative definition, just with a 3 plugged in for a instead of the ones here. So that'll be limit as x approaches 3, f of x minus f of 3 over x minus 3. Okay, and then just like in this first example, the denominator is ready to go. X minus 3 is part of my formula. The f of x will be filled in with the original formula, 1 over x. And then f of 3, I can just compute. That's 1 over 3 for this function. Okay, so let's plug those things in. That gives me limit as x approaches 3, 1 over x minus 1 over 3, x minus 3. And now we have an actual regular limit to work with. And just like before, if I try to plug in my number, I get 0 divided by 0 as like the limit type. And while that doesn't get me straight to a final answer, that kind of narrows down what I need to do, right? So we said when it's 0 over 0, you have 3 situations. If it's polynomials, you factor them and cancel, like we did here. If there were a root involved, I would do the conjugate trick, but this, because I see fractions, calls for the LCD. So I want to make a common denominator between these two fractions so that I can actually add them together, or subtract them technically. So this will get times 3 over 3, and this will get times x over x. Typically in this step, we just hit each of these fractions top and bottom by the other one's denominator. Okay, so now these fractions are over 3x. That's the common denominator. I have 3 from this top minus x from this top. And then all of this is divided by x minus 3. This is the triple-decker fraction that I really don't like. So I'm going to take a step and just reformat it. So this fraction divided by x minus 3 is the same as this fraction times 1 over x minus 3. So I'm going to keep the top fraction and then write that x minus 3 kind of off to the side. Not required, but it really helps me see the cancellation that I'm about to have. So to be able to plug in 3, I need x minus 3's top and bottom to cancel. And this one's ready to go. It kind of has its own implied set of parentheses around it. And then up here, we have almost what we need. We have 3 minus x. So that 3 minus x, I can factor out a -1 like we've done before. That turns the 3 into a -3 and the negative x into a plus x. And of course, -3 plus x is the same as x minus 3. So I'll continue down here. I'm just going to write it reformatted. And now I have x minus 3's perfectly canceling. And that's all that was holding me back from plugging in 3. So I can plug in 3 for my x that remains. And I get negative 1/9 as my answer. So in this case, f prime of 3 is negative 1/9. And because this limit exists, because it actually equals a number, that means that this f of x is differentiable at 3.